Okay, good morning everybody, and welcome back to Math 105. Plan for today is to finish off Standard 12 by talking mainly about Postulate 5 today, and some of its consequences. I've got my usual office hours, today Wednesday at 10 o'clock and at 2, and tomorrow at 10 o'clock and at 1:30. As far as homework goes, I plan, the Standard 12 quiz is up. I need to make it so you can see it. But the Standard 12 quiz will be up very soon, probably for most of you watching this video by the time you're watching it, and will be due on Wednesday evening. Any questions or comments before we get started today? So, are monsters, do you think, good at arithmetic? In general, I would say monsters are not good at arithmetic. Not unless you count Dracula. Okay, so when we left things off last time, we had talked about Euclid's Postulate 5, which is very long, and I'm not going to write it all out on the board. But it says that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles. So in this case, the idea is that we have three lines, one of which kind of goes between one point on the first line and the other point on the second line. And if the interior angles on the same side add up to less than two right angles, so in this case, I would say this angle plus this angle are going to add up to less than two right angles. In other words, if the angle ABE plus the angle BED add up to less than two left angles, then the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. So in other words, saying, since these two angles are on the left of the line BE, that means that if you were to extend the top and bottom lines out to the left, they would eventually have to intersect. There would be a point where if you were to continue them out to the left, they would eventually intersect. Then extending the top and bottom lines to the left would cause them to intersect. Whereas if you notice, these two angles on the right, CBE and BEF, those would both be angles where if you were to add them up, they would get you greater than two right angles. In other words, they would sum to more than 180 degrees. But if we were to extend the two lines out to the right here, they would not actually intersect each other. And so Postulate 5 just says, if you happen to be on the two sides where they add up to less than 180 degrees, then the lines will intersect if you continue in that direction, but they won't necessarily if you have a side where they add up to more than 180 degrees. And of course, Euclid himself never used the notion of degrees, never said anything like 180 degrees. For Euclid, that just meant if you were to extend, he just used the notion of two right angles. Again, using the idea that all right angles are equal from Postulate 4. So, do you all have any questions or comments on what Euclid Postulate 5 said?
This might be really stupid, but you wrote left angles. Am I misreading? Is that supposed to be right angles?
That is indeed.
Thank goodness. I was really worried that I was just completely losing it.
If ABE and BED add up to less than two left angles. Right angles are totally a thing. Left angles are not a thing. I don't know. I'm guessing the reason why I wrote left is I was already thinking ahead to, we're going to extend them out to the left.
Okay.
But You're absolutely right. That was a silly typo on my part. Thanks for catching that. Any other questions or comments? So this postulate, out of all the postulates, is kind of the only one to have its own special name. It's called the parallel postulate. And I think this is where we left off last time. I'd given you the name parallel postulate, but didn't talk at all about why does it have this special name. It's interesting because if you look at the statement of the parallel postulate, Postulate 5, the statement doesn't say anything at all about parallel lines. It's mentioning straight lines, interior angles, less than 2 right angles, straight lines produced indefinitely, 2 right angles, never mentions parallel lines. So I wanted to start out today by talking a little bit about why is this called the parallel postulate if it doesn't make any explicit reference to having parallel lines. And to do that, we're going to need a definition for what it means for 2 lines to actually be parallel. So I screwed up. If you're following along in the packet, I gave you a definition for, I didn't give you Euclid's definition, I gave you a modern definition for parallel lines. I should have given you Euclid's version. And so I'm going to write down a new definition on the board of what it means for lines to be parallel. So question, which of these pairs of lines, the pair on the left or the pair on the right, would you intuitively say look like they are parallel?
The left.
Why?
Because it looks like they will go on forever and ever with that I see they've gotten points. But if you did continue them, they'd go on forever and ever without hitting each other both ways.
Okay, so you're saying if we were to, you're saying basically no matter how far out we were to extend these 2 lines, assuming I draw them perfectly straight, they would never touch each other?
Yeah.
Whereas these do not actually intersect, but if we were to continue this top line going downwards, would intersect the bottom line? Yeah, that's exactly right, and that's exactly how Euclid defined lines to be parallel. He said 2 lines are parallel basically if you can extend them if no matter how far you extend them, they'll never intersect each other. Keeping in mind that just because 2 of Euclid's lines don't intersect to begin with, doesn't mean you couldn't extend one out and suddenly it intersects the other. So here's Euclid's definition, is that parallel straight lines are ones which, being in the same plane and being produced indefinitely in both directions, do not meet each other in either direction. Meet one another. It basically means the same definition as the modern definition I included in the packet. The key difference is that in the modern definition, lines already extend forever in both directions, according to the modern definition of lines. And so you wouldn't have to mention anything about producing them or extending them indefinitely, because they already go on forever. So that would make this pair of lines parallel on the left, but this pair of lines on the right would be not parallel, because even though they don't intersect each other to begin with, you could extend them out. You could extend this top line down and it would intersect the bottom. Any questions or comments about parallel lines? So now that we know what parallel lines are, I'm going to kind of bring that back into looking at Postulate 5 and said, this postulate doesn't make any mention of parallel lines, so why would this be called the parallel postulate? And the reason is, it's going to ultimately come down to there only being one single case where the left angles don't add up to more than 180 degrees and the right two angles don't add up to more than 180 degrees. So here's my question to you. What would have to be the case for these lines in this scenario if the angles on the left didn't add up to more than 180 degrees, the angles on the right didn't add up to more than 180 degrees, and keeping in mind that these four angles are going to have to add up to 360 degrees in total?
They're all 90 degrees.
If they're all exactly 90 degrees, they don't have to be 90 degrees, but they do have to come in pairs that add up to exactly 180 degrees on the left and exactly 180 degrees on the right. So let's look at an example of that. So the only case where you're not going to have the two lines meeting up if you extend them out to the left or to the right is when you have a scenario like this, where angle ABE plus angle BED equals 180 degrees. And if angle CBE plus angle BEF is equal to 180 degrees. So in other words, if these two angles add to 180 degrees, and if these two angles add to 180 degrees, that's going to be the only time that would cause these two lines to not intersect if we were to move them if we were to extend indefinitely to the left or to the right. When the top and bottom lines would never intersect if extended to the left or right. And if these two lines, the top and bottom lines, never intersected, if we were to extend them out to the left forever or to the right forever, what could we then say about these two lines?
Parallel.
By definition, that's exactly what it means for these two lines to be parallel. I.e., the top and bottom lines are parallel. So the reason why this is called the parallel postulate, even though it doesn't explicitly mention parallel lines, is because it's sort of related to the idea of two lines being parallel, in that if you were to extend the top line to the left and right and the bottom line to the left and right, if they do intersect, because the angles add up to less than 180 degrees on one side, then they're not parallel lines. And if these two lines never intersect because the left angles and the right angles both add up to exactly 180 degrees, then the two lines would be caused to be parallel. And so that's why this postulate kind of has gotten a special name over time, the parallel postulate, mainly because the other postulates you can kind of quickly refer to as saying, oh, the postulate about right angles, the postulate about circles, the postulate about drawing a straight line between 2 points. The parallel postulate is much more of a mouthful, and so the easiest way to refer to it is just by giving it its kind of special name of the parallel postulate, the postulate that relates to parallel lines. Any questions or comments about parallel postulate and how it relates to parallel lines? So, for this postulate, I did want to give both Euclid's version and the modern version to you. So let's take a look at the modern version of the parallel postulate and see if you can do a little bit of comparison to how does it look different from Euclid's version. So if we look at the modern parallel postulate, what it says is that for every line L and for every point P, that does not lie on L, there exists a unique line M through P that is parallel to L. So in other words, if I have a line line L to start with, and here, given that this is a modern version of the postulate, we're going to use the modern definition of line. Line is something that extends out forever in both directions. Let's say this is our line L, and this is a point P that happens to not be on the line L anywhere. What the postulate is saying is there should exist a unique line M passing through P that is parallel to L. In other words, there's only a single line. We can find exactly one line that happens to both be parallel to L and then passes through the point P. And that unique line M would look something like this. It passes through P and is going to be parallel to the line L, meaning M and L never intersect each other. How does the modern version of Postulate 5 look different from Euclid's version? Euclid's version sort of relies on, we have these three lines, and if you have interior angles on one side that add up to less than 180 degrees, and extending the two lines out in that direction would cause them to intersect. The modern version says if you have a single line L and a single point P not on that line, then there's a unique line M that passes through P and that also happens to be parallel to L.
The modern one kind of just tells you they exist. With Euclid, you can actually figure out if two given lines are parallel.
True. Euclid says something very specific about two lines that already exist and tell you, hey, here, if you have two lines that exist and a line that goes between them like this, here's a criterion for determining whether or not these two lines are parallel. And if they're not, in which direction, if you were to extend them out, are they going to intersect?
Also, Euclid deals more with characteristics of the lines you already have, which can be parallel in a specific situation, whereas the modern one deals more specifically with finding that parallel.
Yeah, modern version is sort of telling you about something, about a way to sort of find a line that's parallel to L. In particular, it says there's only one way to find a line that's parallel to L, and that also happens to pass through a specific point P. There's infinitely many lines that are parallel to L. To draw a line like this, line like this. There's infinitely many I could draw that are parallel to L, but only a single one will pass through the point P.
It seems to match up with Euclid's other four postulates more. Like this one's very specific, and like it goes into all this detail about the different angles and how you could tell if it's less than 30 degrees. Whereas this is more of like a concept, just kind of stating the truth about parallel lines, which is more consistent with the rest of Euclid's four postulates.
That's a really nice observation. The modern version actually feels, at least to me, a lot more like Euclid's first three postulates than Euclid's own version of the fifth postulate. Because this version of it is giving us some sort of construction method. It says, given a line and a point down on the line, you can construct exactly one line that passes through that point and that's parallel to L. It sort of feels like Euclid's first postulate in a way. And that Euclid's first postulate says that given any 2 points, there's a unique line between them. This is also making a claim about there exists a unique line that you can draw that does blah, 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 satisfies some conditions. And so what's kind of interesting, and what you all are getting at, let me start writing some of this down, is that unlike with kind of the different modern and versus Euclid's versions of the previous four postulates, which were all pretty similar, just kind of written with different language and fixing a couple of Euclid's mistakes, but we're basically saying very similar things. Euclid's plus the modern and the modern postulate 5 are very different from each other. And that they both sort of have some relation to parallel lines and lines that intersect or do not intersect. But that's about it. Otherwise, they feel very different in terms of flavor. So they're very different, other than both relating to parallel lines. And that the modern version feels much more like Euclid's postulates 1 through 3. In that it's constructive in nature, rather than describing how things that already exist interact with each other. So if these two versions of the postulate are so different from each other, why is it okay to call this version the modern version of what Euclid already had? It turns out it's okay to kind of call Euclid's version of the fifth postulate and the modern version kind of referring to the same basic postulate, and that it turns out that Euclid's version and the modern version are mathematically saying the same thing. Meaning if one of them is true, the other one has to be true, and if one is false, the other also has to be false. And so, if you think back to some of our earlier standards, how did we refer to two mathematical statements like this that have the relationship, if one's true, the other's true, if one's false, the other is false?
Logically equivalent.
They're logically equivalent. So it's actually difficult to prove, so we're not going to prove this, but the modern version of Euclid's fifth postulate and Euclid's version turn out to be logically equivalent statements. They're logically equivalent, meaning if you know that one of these is true, the other is true, if one of them is false, you can prove that the other one is false. Which is interesting because Euclid chose not to prove this statement at all. Remember, this is a postulate, meaning Euclid just took his version of the statement about two lines, right angles adding up to less than 180 degree angles, blah, blah, blah. Euclid just chose to take that on faith. He didn't justify this fifth statement in any sort of way. He just said, I'm going to assume this is true, and then build some stuff off of it. But if you knew that the modern version of Postulate 5 is true, you could use it to prove Euclid's version, or vice versa. If you knew Euclid's version was true, you could construct a mathematical proof that this version has to also be true, and if the modern version is true, you could construct a proof that would show that Euclid's version is true. Euclid chose not to take it on. Euclid just chose to take it on faith and not try and come up with any sort of proof of his fifth postulate. But if you knew that this statement right here was true, you could use that to actually prove Euclid's statement would also have to be true. Any questions or comments about the relationship between the two versions of the parallel postulate? So, out of all five of Euclid's postulates, geometers, kind of over the last 2,500 years, have for the most part been okay with the first four postulates. That given any 2 points, there's a unique straight line between them. Geometers caught on pretty quick to the fact that Euclid was missing the word unique. But after adding the word unique, they were basically okay with Euclid's first postulate. They were okay with Euclid's second postulate, that given any line, you can extend it out by whatever length you want. They were okay with Euclid's third postulate, that you could draw any circle, you could draw circles with any center point, any radius that you would like. They were okay with Euclid's fourth postulate, that all right angles are equal. This is the postulate that geometers have hated. That's vexed them, and that they've had basically a big problem with kind of throughout the ages, and saying, I like these first four postulates, but this parallel postulate, it doesn't feel right. It doesn't sit right in their gut. So why do you think that geometers would feel less comfortable with the parallel postulate than the first four postulates? Any ideas?
This is not, as we always said, constructive. It is something they would want to see proven.
It's true that this is not constructive, but the fourth postulate also wasn't constructive. Fourth postulate just says, if you happen to have two right angles, then they must be equal. I make no claims as to you're able to actually construct right angles. But the second half of what you just said, I think it's really close to the truth. This is something they would like to see proven. To most geometers, the fifth postulate feels like it should be a proposition, something that should be able to be proven using whatever postulates one proposes, rather than something that you can just assume is true. And so I would say, why is the parallel postulate considered controversial? It's because to most geometers, postulates or axioms should feel intuitive and obvious. Or let's just say intuitively obvious. Like all right angles are equal. Yeah, duh. Or you almost want to think. Anytime you see two right angles, they're always going to have the same basic shape to them. You can pick one up and drop it on top of the other. The first three postulates, the constructive procedures, yeah, of course we can do all of these things with lines and circles. We have straight edge and compass after all. We should be able to connect 2 points in a straight line, make lines longer, make circles wherever and however big we want them to be. But the parallel postulate does not feel intuitively obvious. It's a lot longer, there's a lot more pieces involved in it, and then you have to have 3 lines and interior angles and adding up to less than 180 degrees. There's a lot more pieces going on, and so the fifth postulate feels like it should be a proposition rather than a postulate. Parallel postulate feels much more like a proposition, which is something that needs to be proven, rather than a postulate which is something that you just assume is true. So here's another fun fact. The first 4 postulates get used by, I think, proposition 6 in Euclid's Elements. Within the first 6 propositions, the first 6 things Euclid tries to actually prove, he ends up using all the first 4 postulates. Does anybody want to make a guess as to what's the first proposition that Euclid uses the parallel postulate in? How far into the elements do we need to get? I'll give you a hint. It's somewhere between 1 and 45, which is number of propositions in the first book. 29. So Euclid uses the fifth parallel postulate way less than he uses the other postulates, and it takes him way longer to have to rely upon it. It doesn't rely on the parallel postulate until proposition 29. He's able to go through his first 28 proofs without ever having to rely on the parallel postulate. Whereas the other postulates all have gotten used many, many times before getting to proposition 29. And why do you think Euclid might, and this is going to be pure speculation because we don't have Euclid's thoughts recorded or anything, but why do you think Euclid waited so long to use the parallel postulate? Sort of, any ideas as to why you think this postulate he might have had reason to wait so long and to really pause before using it?
Maybe you wrote it later.
Maybe he wrote it later. There is actually there are some scholars out there who have suspected that the parallel postulate wasn't even written by Euclid himself. That was written by someone shortly after Euclid, and then was just kind of attributed to him later on. That's certainly a possibility. What I think more modern geometers have kind of guessed to be the case is that they think that maybe Euclid was also not comfortable with the parallel postulate as he was with the others. Parallel postulate, after all, being something that much less intuitive than the first four postulates. But it could also be for the reason he said. Maybe he just wrote it later. Or maybe Euclid, didn't write it at all, and that was something that someone else added to later. We just don't know enough about Euclid, the man himself, to really be able to say one way or the other what was he thinking, why didn't he use it. But there is kind of, I would say, the most common belief among modern mathematicians is that Euclid just wasn't comfortable using it and tried to hold off as long as he could. But that is a big maybe, in that that's total speculation. Euclid never recorded his thoughts or anything on how he constructed the elements. This is all kind of taken from second and third hand sources, and more along the way. That is one annoying thing about Euclid, is we don't really have any primary sources that tell us anything about the guy. So, parallel postulate, what has had its special place with geometers, and that one of the holy grails of geometry for thousands of years was geometers trying to answer the question, I don't like this fifth postulate. It feels unintuitive. I'd rather not assume this if I can help it. The first four postulates I'm okay with. Is there a way to prove the parallel postulate using just the first four postulates? So in other words, assuming only the first four postulates are true, is there a way to prove the fifth postulate? And geometers for thousands of years tried to say, can we actually construct a proof that ultimately only relies on the first four postulates, as well as various laws of logic, including Euclid's common notions? Can we actually prove the fifth postulate as a proposition rather than just assuming it as well as just a postulate? And it turns out the answer is no, sadly, as proven in 1868 by Eugenio Beltrami. So Beltrami was an Italian mathematician in the mid-1800s. He was actually able to prove that you can't prove the parallel postulate if your starting assumptions are just the first four postulates. You could do lots of things using just the first four postulates. You could prove lots and lots and lots of Euclid's propositions, including all of the first 28 of them. But one thing that you can't prove from the first four postulates alone is the parallel postulate. Whether that be Euclid's form of it or the more modern version of the parallel postulate, which is the one that Beltrami would have been studying. So, it's kind of weird asking the question of how do you prove that you can't prove something? It's sort of a weird question in that, like, how do you prove you can't prove something? Do you write down all possible proofs and show none of these work? Theoretically, there's infinitely many proofs you could try and write, so that's kind of hard to do. So what Beltrami actually did to prove you can't prove the fifth postulate is he showed that the first four postulates and the fifth postulate are logically independent of each other. Postulates 1 through 4 and postulate 5 are logically independent. What do you think that means? Logically independent. We've seen logically equivalent before, and then two statements are logically equivalent if one is true implies the other is true, and if one is false implies that the other has to be false. But along the same lines, if you had to guess, what would you guess that logically independent meant in talking about kind of the first relationship between the first four postulates and the fifth?
That the first four being true or false has no bearing on whether the fifth one is true or false.
Well said. The first four being true or false has no being on whether the fifth is true or false. And how you would actually show that was very complicated. We're not going to prove that in here, that their first four postulates and postulate 5 were logically independent. After all, that's something that took Beltrami. I'm not going to say I almost said it took Beltrami thousands of years, but that's implying that Beltrami was thousands of years old. It's something that took geometers thousands of years to do, is to prove that they're logically independent of each other, that you can't that if one is true, or if the first four are true or false, that has no effect on the fifth being true or false. I will say that the general outline for how Beltrami did this is he showed that he could construct a set of rules in which the first four axioms in which the first four postulates are true and the fifth postulate is also true. And he also showed you could construct a set of rules where the first four postulates are true but the fifth postulate is false. Dr. Gerstle, what do you mean by different sets of rules? By different sets of rules, that's going to be something we're going to look at in the last three standards. How could you look at different sets of geometric rules where the parallel postulate suddenly is no longer true, but the first four are true? Whereas for the next several standards, we're going to be looking at the case where the first four postulates and the fifth postulate are all true. And that's the usual way that you would think of geometry working. Any questions or comments? So the parallel postulate has sort of been this geometric enigma throughout its history. And a lot of modern geometry is built around the idea of how can we construct definitions for points, lines, and circles in ways that would make the first four postulates true, but the fifth postulate false.
When did they start using 360 degrees in geometry?
Like when did the notion of how to measure angles using degrees and such come about? Mm-hmm. That was a few hundred years ago. So not recent per se, but a lot closer to now than to the time of Euclid, I would say. I don't remember offhand. Do I remember who established kind of I don't remember who established kind of the notion of degrees. And then I think degrees came first, and then radians came after that. But I think that system of measuring angles and such actually came about from cartographers, from map makers, in other words, and kind of like the age of exploration, like in like the 1600s. That's kind of where the idea of like degrees and such came from, rather than from mathematicians. Mathematicians just kind of adopted that idea and took it into geometry at the time from the kind of the measurement system that cartographers were coming up with and explorers. Yeah, that's a good question. Any other questions or comments? In that case, that's going to do it for Standard 12. So we have one more standard, Standard 13, which I'm guessing will take us like a class and a half-ish to get through. Where Standard 13 is going to be about the common notions. We're going to look through each of Euclid's 5 common notions, which are the kind of laws of logic that Euclid just assumed to be true. And then finally, after that, meaning sometime on class on Friday, we'll start looking into actually proving the propositions. And that'll be when I ask you to start bringing your copy of Euclid's Elements to class, because we're going to have to start looking at some longer proofs that I don't want to have to write out on the board because they're long, and I don't want to spend the entire class writing proofs on the board. All right, hope you all have a good day, and I will see you all on Wednesday. Nice job today.